An electronic component is mounted adiabatically at its base. The component dissipates 51.2 BTU per hour. Okay, it's losing heat at this rate, and the ambient air and surroundings are at 75 degrees F. Assuming a constant heat flux and average radiative heat transfer coefficient of, so H radiation is 1, and an average convective heat transfer coefficient of 1.25. Okay. The surface temperature of the component is most nearly, so we want to find the surface temperature. So first thing, I'm going to write my heat transfer equation, which is Q is equal to AS times delta T. Delta T is just Ts minus T infinity all over the total heat transfer resistance. AS is equal to, so for the surface area, we're going to do all these sides in the top. We're not going to do the bottom because that's adiabatic. This is 2 times 4 plus 5 for the top and 4. This equals to 52. And if we convert that to feet, okay. Now to find R total, okay, I'm just going to do a resistance diagram. Okay, so the convective and the radiation heat transfer coefficient happen at the same location. Therefore, this is parallel resistive. The formula for R total for parallel looks like this. R radiation plus 1 all over R convection. And if we rearrange and solve for R total, it looks like this. Okay. Now for the resistance of radiation. So R radiation is equal to 1 all over H radiation, which is just 1 over 1, plus, and similar with the convection, 1 all over 1.25. If I put this in my calculator, zero 0.44, and the units are, okay, hour, feet squared, degrees F, and BTU. Okay, so I think we have everything. Let's check. So we found R total, we found the surface area, this was given, T infinity was also given, so we can solve for TS. So we got to do a little bit of algebra. Okay. All right. And Q is equal to 51.2 BTU per hour. our total okay, and the surface area was 0.36 feet squared plus T infinity is 75 degrees F. TS. So if I put this in my calculator, T1.2 times I get 137.6 degrees F.